Here we have another statics problem. We've got a girder and we're going to try and work out these unknown values of T1 and T2 here. Okay, so these forces, these tensions in these cables that we've got here. Okay, this time we've got a girder at an angle hanging from a hook. So presumably these are some cables here supporting it, and we assume that they have negligible weight or mass. Now, the situation we've got here then is, obviously, we're assuming actually that this girder at the moment is just hanging from the hook. It's not moving up or down, it's just hanging, just suspended in the air. And as a result of that, we can therefore sort of deduce that we've got this upward 16.5 kilonewton force, this force of tension in the cable here. And then we've got these tension forces acting here. So they're pulling down on the hook. This cable's pulling up on the hook. So the hook is the object we're considering. So you've got three forces here acting at this one point. They're in the same plane, but in different directions. And what we can deduce here from the fact that this is in equilibrium, because it's static, so it's static, it must be in equilibrium. These forces must, well, basically the resultant force on this hook must be zero. So the resultant force on the hook must be zero. So that's the starting point for this question. Right, so there's a couple of different ways we can do this. I'm going to show you the first method. The first method is to use a vector triangle. So we've seen this method before. So we've got three forces here and we're going to draw them into a triangle. So we're going to take the vectors and put them head to tail. So if we start off with T2, or actually let's start off with T1. So we can draw T1 coming down like this. It doesn't matter if the angles aren't exactly right. We don't need to get a protractor out, just a rough idea. And then we're going to draw T2. Now, the interesting thing here is this is 30 and this is 60. So we know that the angle between T1 and T2 is actually 90 degrees. So I'm going to draw T2 across here like this. Okay, I'm going to put that there. And it might not be exactly 90 in the diagram, but we're going to draw 90 anyway. Okay, I'm just going to make this one a little bit longer. Now, we can then draw, so we've gone head to tail, and then we've got head, and we're going to put that to the tail of this 16.5 kilonewton force. So this is T1, this is T2, and now we've got the 16.5 kilonewton force. Now, obviously this should be completely vertical. My diagram's not perfect, but as long as it's about right, it doesn't matter, okay, because we're not drawing a scale diagram here. Now, we know that the angle between T1 and the vertical, this 16.5 kilonewtons force, is 30 degrees. So we know that this angle here is 30 degrees, and this one would be 60, but we're not going to worry about that one. We're going to use this angle. So now we've got a right angle triangle, and we just need to work out the adjacent. So this is the adjacent and the opposite. So T1 is the adjacent, T2 is the opposite of this vector triangle, and obviously this is the hypotenuse. So we're just going to use some simple trigonometry now. So what we can say here then is that if we work out T1 first, we can use cos theta for this one. So we can use cos of 30 is equal to adjacent over hypotenuse, so T1 over 16.5, and we know it's in kilonewtons. So if we rearrange that, we're going to get T1 is equal to 16.5 cos 30, and then we can work that out obviously using our calculator. So if you take your calculator, put that in, 16.5 cos 30, you're going to get 14.3. So that's 14.3 kilonewtons. And then to work out T2, we're going to use opposite of hypotenuse. So we're going to use sine here. Sine of 30 is opposite over the hypotenuse. And if we rearrange that, we're going to get T2 equals 16.5 sine 30. And that will equal, make sure your calculator's in the correct mode, that it's in degrees, not radian. That will give you 8.25, and that's kilonewtons. And there's your answer. So we've now worked out these unknown values here. There we go.